And so Matthew had a question about the Wireshark Lab 3710. By the way, I'm caught up on grading. I know, Ken, you had several that you wanted to have items, and I asked you if you will just put them in a Word document, and then I will answer those. And I'll go over those maybe on Tuesday if you want me to do that. But one of the things that Matthew mentioned is that in this lab is having trouble seeing traffic. And what I think it probably was more than likely is when you open up Wireshark, one of the things that Wireshark does, there's a couple things. One is if for some reason it doesn't open as admin, so user account control, if you click yes, you have to click yes so that it will actually load the drivers for the promiscuous mode on the NIC. The other thing you're going to see is that there are going to be a large number of network interface cards in here. And if you don't select the one that is actually connected, then you won't get any traffic. And then the way to tell which one is connected on here and in the real world is look for the one that's got a heartbeat. And you can see here, the local area connection is the one with a heartbeat. So if I wanted to grab traffic, I need to pick that as my network interface card. So now if I go in here to actually capture traffic, I'm gonna stop capturing here. I'm gonna start a new capture. Not gonna continue without saving, but I'm gonna do an IP config release renew. IP config, oops, I can spell it right. I'm actually typing with two hands, which is again a miracle. But there's the IP config release renew. And if it works, which it should, because the router is supposed to be handing out DHCP addresses, then we should see, or at the very least, yep, we got that. So now we can go back over to Wireshark, stop our capture, and actually filter by DHCP. And you will see here's the release that I sent. So this was my machine 1.147 sending to the router saying I want to release my address. And then here is my renewal. So I sent out to discover, DHCP discover. The router at 1.1 gave me an offer. And in fact, you can drill all the way down in the offer and it will show you what the offer was. It offered you the 192.168, or offered me in PCA, 192.168 1.147. And it even goes on down and tells you what the lease time is. So here we can see our lease time of 1 day. If there's any other items, any options set, they're set in here too. So you can actually look at all the different options that were set in the offer. And then here's my request, and then finally an acknowledgement. So you can see that the discover and the request are both broadcasts, and the offer and acknowledgement are actually unicast. Now, again, the reason you probably weren't seeing anything at all, Matthew, is because when you opened up Wireshark and that very first thing and you're choosing an interface, you must choose the interface that's got the heartbeat. Does that help?
Oh, it was. I think on the next one, it worked, but I don't think it worked on that one.
Well, the reason it worked probably is because you maybe only had one network interface card showing up. And so that's why it worked. But you'll see that for the most part, you've got just this local area network one that's got traffic on it. And if you pick it, then you can do that. You also have the ability under capture, when you stop a capture and you want to start a capture, you can change the interface by going into, I believe that's a filter, but there's a way to change the interface if you want to. But pick that local area connection, and that will be more than likely will give you the traffic you need. And even you can see here we're getting traffic because it's on this network showing what it's seeing across this link.
All right, I'll try to do that live again tomorrow and see if I can get it to work.
Yeah. The other thing I've also seen, especially on real PCs, if you've got it installed, if for some reason it doesn't run or doesn't escalate the privileges, you can always right-click on it and run it as administrator, and then say yes. Because I've seen that on PCs in the lab. I've seen it not want to run at administrator level, and if it's not running at admin level, it will not load the promiscuous NP-cap drivers that are needed to do capturing. All right. So I think that might be what the issue you were having with 3710. Also, folks, I want to tell everyone you're doing a great job on the net labs. I'm very proud of you. I know to begin with, we had some folks who were turning in labs and weren't doing them in net labs, but everybody's on board and we're working hard and doing well on that. So I greatly appreciate that, and do greatly appreciate you trying to stay caught up and working. I also want you to know again that we've got 2 months left. So we're still in pretty good shape time-wise. I want to do some things about looking at, we talked about the data link layer. We talked a little bit about the data link layer and framing and those items. We talked a little bit about the physical layer. The Ethernet switching, you did it. I'm fairly comfortable that you can read that and understand it. But if you have any questions on it, let me know. I do want to move into the network layer, and I want to jump forward a little bit because I want to talk about, we talked about our models. We've talked about how we can look at the different layers of the model, and we talked about, I'm gonna go over here to another page. We talked about the application, presentation, session. Let me go ahead and type these out. Presentation, session, transport, network, data link, physical layers. This is the OSI model. Okay, so the application, let me type that in here. And then we talked about how the physical layer is our bit pusher. It's our layer 1. It's bit pushing. I'd give you a great example of this one. Yesterday, we put a new VLAN onto our data center switches. We were moving a server over to another rack. So we moved that server, plugged in the cables, and we were not getting a link on the switch. So when you look at a switch, there's a couple ways the interface can say. So if you do a show interface or show IP interface brief, show IP interface brief, that you will see a status of layer 1 is up, or you can see up, you can see up, down, you can see administratively down or admin down. We had a situation of basically up, down. In other words, we were seeing I could even see the type of SFP, and that's a special little, basically a small NIC-like device that slides into a modular switch. I could see that a 10 gigabit SFP was in the actual slot, but layer 2 would not come up. And we couldn't figure out why, and come to find out what was going on was we were plugged into the wrong NIC on the back of the server. So guess what? It was a physical layer issue. It was a layer 1 issue. And that again is typically power and cabling issues. And so one of the things I always teach my students in the classroom, and you need to know this too, is when your students are doing labs in the class, if everything looks like it's right and things still are not working, check cabling. Because the number of times I've seen people accidentally have the wrong cable type or the wrong cable plugged in the wrong port, and that is the problem. It just happened to us yesterday. So to give you a great example. Now our data link layer, we talked about breaking it into 2 different layers, the logical link sublayer, and there's another layer here. Go ahead and tab this over so we're in the same spot. And it's called the media access control sublayer. All right. Now, these 2 layers are very important because you'll notice you can pick up a piece of cable. You can pick up a network interface card. So now we're getting up into the media access control sublayer. You cannot, however, pick up an IP address. And so the data link layer has these 2 sublayers, and this is the boundary between the physical and the logical. So basically from here up, we've got logical components. And then down here, we've got physical components. Now, a great example of this, what is a MAC address? Anybody remember that portion in the curriculum? What is a MAC address?
Physical address.
Exactly. It's a physical address. It is burned into the NIC. So that's a physical address that you really cannot change. You can spoof it, by the way. You can do it with software and spoof it, but you can't physically change what's on the NIC itself because it's burned into the NIC. So that's part of this sublayer, and you plug the cable into a transceiver that is a layer 1 on the NIC. So we're right here. So since we move up to here, and we're going to be talking about IP addresses, okay, when we get here, now we're into logical addresses. In other words, there's no reason in that lab we just looked at, there's absolutely no reason that this IP address is 192.168.1.147, other than that's what was chosen for the lab. Has nothing to do with the physical nature of this PC. Likewise, if I do an IP config /all, you'll see here that the physical address does have to do with the physical nature of this machine. In fact, I'll show you something cool. Remember, immediate access is the first 24 bits is what's called the organizational unique identifier. And then that's the first 24 bits. And then there's 24 bits that are the serial, basically the serial number from the manufacturer. Okay. So watch this, you'll see something cool. We can go in here and we can take this address 00155D, and we'll go over here and we'll do MAC OUI lookup. And we're gonna put in 00.15 and what was it? 5D. And it's gonna come back, or should come back, as VMware. Oop, Microsoft. Comes back as Microsoft Corporation. Okay, so it sees it as a Microsoft address because it's using a Hyper-V adapter. Okay, that makes sense. That's a Hyper-V adapter. I was looking at, I looked at the wrong adapter. That's a Hyper-V adapter that's part of this. Let's go back up here to 00, the actual local area connection. Let's go to 005056. 0050-56. This should be VMware. Yep, there we go. So there's VMware Corporation. So one of the things hackers can do is they can just find out the MAC address of a machine, and that will tell them whether or not it's a virtual machine. Because that tells me immediately, hey, that's a virtual machine, because the organizational unique identifier is VMware. One of the problems you'll find sometimes, by the way, with virtualized PCs is if you clone them and you don't change the MAC address that's made by VMware, you'll end up with the same MAC address on multiple machines. We actually had that issue when we first rolled these PCs out, and that was a major issue because all the PCs had the same MAC address. We had to go in there and have it recreate a new MAC address for each one of them. But that media access is based upon the physical nature of this device. When we move up into our network layer, we're going to be looking at layer 3, and we're going to be looking at 2 protocols in particular. We're going to be looking at IPv4 and IPv6. Now, IPv4 has been around a long time, and it is, I'm going to go ahead and show you my little thing that I always show my students. I'm going to take this away, by the way, so we won't have quite so much. It is a 32-bit address, usually shown in dotted decimal. So again, example 10, 10, 10, 1. Is this big enough, everybody, or I need to make it a little bigger? A little bigger?
Large enough for me.
Okay. I'll make it just a tad bigger. That way it won't. And then get rid of this here. Okay. So 32-bit address shown as dotted decimal. Each IP address consists of a network portion, an optional subnetwork portion, and a host portion. So when I go in here, all right, so there's a network portion, there's an optional subnetwork if you happen to be subnetting it, and we're going to get into subnetting definitely, and then there's a host portion of the address. Now, how do you determine what portion of an address is the network, the subnetwork, or the host portion? You do that by the subnet mask. So in other words, If I handed you just the address 10.10.10.1 and didn't tell you anything else, you can make some assumptions if you were to say it was a classful address, all right? Because this is what you're going to learn is called a Class A address. However, if I didn't give you any subnet mask, you really can't fully tell me what portion is the network, what portion is the subnetwork, and what portion would be the host, okay? But if I give you an address like this, 192.168.12.10, and I give you a subnet mask of 255.255.255.0. Now, I skipped the section on converting from the binary to decimal, decimal to binary, but I hope everyone knows that a octet, this is 8 bits, okay? Each one of these represents 1 bit position, and it's 2 to the 0 through 2 to the 7th. And if for a 255, that is in binary 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Dot. And then for 0, it's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that is telling us that we have a subnet mask of 24 ones and 8 zeros. Now, the mask in the subnet mask, ones are placed in all the portions that are network bits, okay, and zeros go in the host bit portions. So we take a look at this. We take a look again at our example here. By looking at this address with the mask, I can say, oh, guess what? Okay, it makes sense. This first 24 bits, that's the network portion. The last 8 bits, that's the host portion. Now, one of the key things that's mentioned up here is you cannot have all ones or all zeros in the host or in the host portion of the address. So if I gave you the address, I said, okay, everybody, 192.168.12.0/24, which by the way, that means that's shorthand for this mask right here, because it means 24 ones are turned on in the subnet mask, okay? And I said, is this a valid address to be assigned to a host? The answer would be no. Because if you look right here, in the 8 host bits, they're all zeros. This is what is called the network ID. Okay, so that is the network ID. If I gave you the address and I said, okay, what about this one? 192.168.12.255/24. Well, now you can see that there's 1, 2, 3, 4, 5, 6, 7, 8. There are 8 ones in the host portion. So that is not a valid IP address to put on a host, because that, folks, is what's called the broadcast ID. So the usable addresses on the network 192.168.12.0/24 are from .1 to .254, because that's the only addresses where they're not all ones or all zeros inside of the host portion of the address. Okay, I'm going to stop for a second and ask if there are any questions.
I have none.
Has anybody ever got an error like this before? I'm going to go in here and I'm going to open my network settings, and I'm going to say, okay, Ethernet. So I'm going to statically assign an IP address, and I'm going to do this right here. I'm going to put in the IP address. By the way, if you ever get this error, you'll know why now. I'm going to put in the address. Okay, I want 192.168.12.0 tab that, and I'm going to say, okay, that's what I want it to be. And you get an error message. And it says its combination of the IP address and subnet mask is invalid because all the bits in the host portion of the IP address are set to 0. This is the network ID, so you can't assign it. Likewise, 255 should bark at you and say it's all ones. If, however, I put .10 in here, it'll take it all day long because that is a valid IP address to place onto a host because the host bits are not all ones and they're not all zeros. Now, it's very easy to tell that what's all ones and all zeros here, but when you get into an address like this, imagine this one. If I put in an address like 172.16.255.0 with this mask, do you think it's going to take it? You
Nope.
think, well, somebody said something, go ahead.
Yeah, no, it won't.
It won't?
I don't think so.
No problem whatsoever.
Oh, okay.
Now here's why. Here's why, and that's why I show you this example. With a /16-bit mask, we have 2 octets for the host. We have 16 bits for the host. Are all 16 bits ones? No, because I've got 8 ones here and 8 zeros here, so they're not all ones. Are all 16 host bits zeros? No, this is a valid IP address. Now, if I did this, it's not valid because now I have all ones in the host portion of the address.
Okay.
But that is perfectly valid because all the host bits are neither ones nor zeros. And that's where things get a little tricky. Here's another example. Imagine this one.
All right.
Is that a valid address or not?
Oh, they're all one.
Correct.
Broadcast.
That's the broadcast. That would be the broadcast for that particular subnet. This, however, would be perfectly fine.
You know, I was taught that we never put 255 as one of the octets. That's what I was taught. But
And that is true. That is true. And the reason you were taught that, and the reason for that is because you can't have all ones in the host bit portion. So that is correct. That's why we don't use it. We don't put 255 in any portion where it's all ones in that portion. But you can use it like this. There's no reason. That's actually a valid IP address. That's a valid IP address. Well, that's a valid IP address. In fact, this is a valid IP address because all the host bits are not ones or zeros. So the only time you don't use 255 is if it's going to make the host bits all ones and all the host bits all ones.
okay.
So that's important as we talk about IP addresses and we talk about our network layer. So let's jump over here real quick and let's look at, again, we've got encapsulation. So we've got our transport layer header, our transport layer information. That's our little Russian die talked about coming down, being placed as data in the network layer. And then we're going to have an IP header on here that's going to contain our IP addressing information. So here's a couple things about IP, both V4 and V6, that people find kind of strange, but there's a reason for it. IP is connectionless. It is best effort, which means it will try its best to get it there, but it's not going to guarantee delivery. It actually relies on the transport layer for guaranteed delivery. The reason for this is because some traffic running on IP needs guaranteed delivery, like transactional data, like accessing a web page. Some doesn't need guaranteed delivery, like voice over IP or streaming media, those types of things. So in order to support both types of connections, they made IP at layer 3 connectionless and said, we'll handle reliability at layer 4 at the transport layer. And we'll talk about that as we move on through the class. It's also media independent, which is really cool. That means you can run IPv4 and V6 over copper, wireless, satellite, you name it. You can run IPv4 and IPv6 across it, which is really neat. Okay. So let's move forward and take just a look at the packet and IPv4 header. Now, this thing is pretty complicated, and it was actually one of the problems that they tried to solve with IPv6 is they tried to simplify the header because each part of this header has to be processed by a router in each hop. So it's a fairly complicated header, and it causes some issues because of it. You're not going to need to know every single part of this header, but it is important to kind of know this especially is a neat item, this TTL, time to live. We talked a little bit about frames, and we talked about, or you've read about frames, and in frames, there's no TTL field or time to live. And so you're going to learn as we move forward in our studies that layer 2 loops are very, very dangerous because there's no frame TTL. With IPv4 and v6, there is a time to live, and every time a packet goes through a router, the TTL is decremented by 1. So typically this is, depending on the operating system, the TTL is 128, or it could be 256, but typically it's 128. And so if for some reason you get to the end of the TTL, the 128, so you're in a loop and you're flying around the routers, when you reach the end of your TTL, you will be discarded. So that's an important difference between frames and IP or logical headers. The other thing here is you'll notice there's a source IP address. So that's a 32-bit field because this is an IPv4 header. And there's a destination IP address. There's flags that tell you what upper layer protocol at layer 4 that you're going to be passing this information up to. And then there's information about fragment offsets and a header checksum, different items that are used just for the maintenance of the packet as it moves across the network. Now look how complicated this is. Again, a lot of different moving pieces on this. And then let's go down and take a peek at an IPv6 header. An IPv6 header, by the way, IPv4 is all the addresses have been used. We do not have any more public addresses in IPv4 available. However, we're all using NAT, so we're still pretty much able to use IPv4 at the moment. We will be moving to IPv6, and that is part of this new CCNA, and it has been for some time. Just to give you an idea, it's 340 undecient addresses, which is supposed to be enough addresses to put an IP address on every grain of sand on the planet. Now that's just phenomenal to even think about, but that's the actual thing that they use as the talking point. Now look at this header. This one is a little bit, I know it looks more complicated, but it's actually not. It's a little less complicated because there's less moving parts inside this header. And I use moving parts in quotes because there's no real moving parts. But they've actually simplified this header a great deal so that there's not as many pieces to it as what you find in IPv4. The result is, even though you've got 128-bit addresses, which makes the header bigger, these headers can actually be processed by routers faster and more efficiently than IPv4 headers. Okay. Now, the big difference here is we do have 128-bit addresses, which make them much, much larger. Okay. It also gives us a much, much larger, there again, you can take a look here. There's the IPv4 header or IPv6 header. How simple it is. There's IPv4, there's IPv6. Look at how simple that is. 1, 2, 3, 4, 5, 6 versus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different headers. So they simplified the IPv6 header so it's much better. Now, layer 3 is all about routing. It's about moving packets from one network to another. Most people don't even know this, but hosts have route tables. Okay. There are route tables on your PCs. Right here, you can see it. If I go over to, let's go back to NetLabs so I can show you. I go back to NetLabs and I do a print route. Let me do this. Let me renew that. Let me get that renewed. Route print, not print route. Brain fart. Do it again. Okay, so there's your routes that are on this particular PC. You can see that on that's the Hyper-V adapter, and then you can see IPv6. Let me go back up to find my other adapter here, okay? So there's a Intel Pro connection right here. You can see that this particular machine is on the 172.617.118 network. Okay, so let me do an IP config here. Okay, so 192 or 172.17.118 here. And it's also on the 192.168 1.0 network. And you'll see that it's on that network right there via 192.168 1.147. So even PCs have their own route table that they will use. And if you try to go to another destination, it will go and look in this route table to see where it needs to go. So for instance, if I'm going to go to PCB, okay, so let's go to PCB here. Let's look up its IP address, do IP config. IP config. So this is 192.168.1.114. So let's go to PCA and let's ping 192.168.1.114. So we got a reply, right? Well, here's what actually happened when I pinged this address. First off, there would have been an ARP request and an ARP reply that would have been sent. Okay, if it wasn't already in the ARP table. You can see that 1.114 is in the ARP table, and it is there dynamically. So it was learned via an ARP request and an ARP reply. If that was not there, it would have been done an ARP request, ARP reply first. Then what it will do is it will take and it will actually look in the route table once it determines what networks it's on. Now, what happens is it takes this address, the destination, and it ANDs it with the subnet mask that is on this PC, on PCA, finds out what network it is on. We'll talk more about ANDing as we move forward, but basically it will figure out that PCB is actually on the 1.0 network. And then it will look in its route table and see how to get to the 1.0 network. And it will see that in order to get to this network, I need to send it out 1.147, which is the IP address that is on PCA. And so then it can send this ping directly over to PCB. Likewise, PCB, we can use the other command, netstat-r. It has a route table, and you can see that it is on the 1.0 network via its IP address of 192.168.1.114. So individual machines, individual hosts maintain their own route tables based upon what addresses are on their interfaces. Questions about that? That's how this router figures out where to send things, or this PC figures out how to send things. If it sends it to something that is not in its route table, then it will send it, if it's got one set, it will send it to its default gateway, which is its way out of its local network. So this is saying if I don't, quad zero, this says if I don't have any other route to it, in other words, there's no other match in this entire route table, send it over to this IP address out of my 1010 interface and hope they know how to get there. And that'll go up to R1, and then R1 would need to be able to figure out how to get to the next hop network. Questions about the host table? Okay. Well, once we get up to the router, it's then the router's job to forward packets. In other words, it's got to decide how to get the packet to the destination. So if PC1, as in this example here, is sending something to PC2, which is on 10.1.1.10, you will see that it will go up to R1, and then R1 has to make a routing decision based upon its route table. And if R1 has a route for the 10 network, okay, it will then forward it to R2. And one of the wild things that happens, and we've talked about this, I know we talked about this in our previous discussions, but one of the wild things that happens at layer 2, R1 rewrites the frame every time, or every router actually rewrites the frame when it comes in. So when it comes in on gig 000, layer 2 information is rewritten when it's sent out gig 001 over to R2. And likewise, it's rewritten again when R2 sends it to the PC. But the router looks in its route table and makes its best, longest match. Now, if nothing matches in the route table, it'll use a default route if there's a default route there. If there's no default route, the router drops the packet and just sends a destination unreachable back to you. Okay. So for instance, let's see if I can pull this example off here. Let's go to, we're on PC A, and in this particular network, we're going here. I'm going to try to ping, an address 204.211.19.18. You'll see I get a reply back from 192.168.1.1 telling me destination host unreachable. And 1.1 is this router right here. And so this router looked in its route table and had no destination for the 204.211.19.18 network, and also had no default gateway set. So it replies with an ICMP destination unreachable to the host. Routers make decisions based upon their route table alone. And just because you have a route to a destination doesn't mean you have a route back. That's a pretty important thing in the route table. You also will see in the router many times there are different types of networks, like directly connected. So with R1 here, any address that is actually assigned to an interface would be a directly connected route inside of the route table when you do a show IP route. If it's a remote network, then it's going to be delineated by either a static route or some type of dynamic routing protocol. So you're either going to put it in there with a static route, which makes it appear like this, IP route 10.1.1.0. The mask of the destination network, excuse me, next hop IP address. You can also use outgoing interface. This would then become a route on R1 or in R1's routing table. Static routes, we'll do a whole lot more with them later as we get into second class and the third class. But static routes are great because you have full control of the path the packet will take. They're more secure because you manually set them. However, they are not able to easily reconfigure themselves when a link goes down. So for instance, if you were using static routes here to send everything that was going to 10.1.1.0, have it go from R1 to R2 with a static route, if that link went down, you would have to put in another static route going through R3. Now, if you've been around networking a while, you know there's a thing called a floating static route that we will talk about. So I could set up a floating static route and make the static route begin using R1, R3. But as we say many times at this point, these are not the droids you're looking for. Move along. Okay. So in other words, we'll get to that later in the curriculum. It's just not talked about right now. Dynamic routing is when two routers run a dynamic routing protocol and then exchange information about the routes that they are connected to and they know about. It's great because it can recover from links going down. It doesn't require manual intervention from you. However, it is less secure, although all modern dynamic routing protocols have the ability to actually authenticate peers. So, but you still have to do that peer authentication correctly in order for it to work. So again, with dynamic routes, if you had the best path was R1 to R2, and and that path failed with dynamic routes, a new route would automatically be placed into the route table, or would be very quickly added into the route table by the dynamic routing protocol. So there's a video here, and here's an example showing the routing table of R1. And we can see connected routes here, these C routes, and that tells you the networks that are directly connected on interfaces, and we can see this here. So R1 should have 2 connected routes, in which it does. And by the way, this local route here, that is something you only see in iOS 15 or higher. And it basically just tells you what the actual IP address is on the interface. So this tells me that 192.168.10.1 is the IP address on gig 000, this interface right here. And 209.165.200.225 is on gig 001, which is this outside interface. This, however, is a remote network learned via OSPF. Now, here's the great thing. Anytime you do a show IP route, if you don't remember what these stand for, just go up here and look. And we'll actually tell you what they are. So O is OSPF. So these 2 routers are running a dynamic routing protocol, and R1 has learned about the 10 network from OSPF. R1 also has a static default route set here, which you can see by the S star. S is always for a static route. Star means it's a candidate default route or a gateway of last resort. Which means, again, that would only be used if no other entry in the route table matches. If a route table entry matches, then that is what is used. If it does not, then it will use the default route if it's available. Questions? Okay, I want to jump over and do one more thing here to talk a little bit about an idea that is not really covered much at all, but we're going to need it as we move forward, just as we can discuss subnetting, because I'm going to discuss classful addressing, and I'm also going to discuss with you classful subnetting. In fact, I'm going to send you a video as part of the video upload of this video that I'd like for you to look at. It's going to be my 7 holy steps of subnetting. But back in the old days, all IP addresses were considered to be part of a class of address. This was based upon the parameters in the first octet of the mathematical parameters of the first octet of the address. So for instance, in the address 10, 10, 10, 10, all right, you can see that the initial decimal value here is 10. So it is a class A address. So if I gave you this and said it is a classful, it's classful, okay? If I did that, you would know that this is a class A. You would also know that the network is the very first portion here, okay? Because in a class A, the first 8 bits are the network bits, and then the last 24 bits are the host bits. Oops, let me change that. Okay, so there's the host bits. And the reason is because I'm telling you it's classful. So for a class A, if you see a 0 to 127 in the first octet decimal, then it is a class A. If you see it in binary and it begins with a 0, then it is a class A. Now, why is that? Now, here's why. I'm going to show you. Think about it. If you put 0, 0, 0, 0, 0, 0, let's see, that's 8, I believe. 1, 2, 3, 4, 5, 6, 7, 8. Okay. The decimal value of that is what? 0. Okay. Now, if we put 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, decimal value of that is 1. If we put 1, 2, 3, 4, 5, 6, 7, 8, actually let's do 1, 0. The decimal value there is 2, and so on and so forth. If we get up to 127, 127 is 0, 1, 2, 3, 4, 5, 6, 7, 8. So that is decimal 127. So everything from 0 to 127 is always going to have a 0 as the first bit position. That's how we get our Class A. Then as soon as we roll over here, as soon as we go to, okay, what about if we have a 1? 1, 2, 3, 4, 5, 6, 7, 8. Ooh, Lord, that's too many. 1, 2, 3, 4, 5, 6, 7, 8. All right, that is 128. Golly, finger dyslexia. 128. All the way up to 1, 0, 1, 2, 3, 4, 5, 6. There we go, which is 191. 1, not 2, 191. So that means anything that starts with a 1, 0 in binary, or the decimal values 128 to 191, that is a Class B. Class C begins with 110, 3, 4, 5, 6, 7, 8, which is 192, up to 110, that's 3, 4, 5, 6, 7, 8, which is 223. 192, 223. And that tells you that is a Class C traditionally. Now this is classful addressing, and we do a lot of things that are not classful anymore. But it is important to still understand classful addressing so that when you see an IP address, if you see a list of IP addresses and you see, you see this, and I say this is classful, 172.16.12.10. Okay, classful. What portion of this address is the network portion? Anybody?
172 and 16.
172.16, because this, folks, take a peek here. If it's classful, this is a Class B address. So the first 2 octets are the network portion. The host portion is the 12.10. All right. So now if I give you 193.225.23.17, what portion is the network portion?
193.225.23.
That is correct, because this is a Class C. Now I would have to again say this is classful and this becomes the host portion. Okay. So it is important to know when we're looking at these what the traditional classes were. Now we're going to do some things down the road. We're going to subnet. As you start reading about the subnetting sections, you're going to see things like this. So that is 255.255.255.0. So this is telling me that the first octet is actually our network portion. Okay. The next 2 octets, because this used to be a Class A, but we borrowed 16 bits. This is now our subnetwork portion. And we've only left 8 bits for our host portion. And so you're going to learn as we move forward and as you start reading, and I want to introduce this now because when you start reading it, I want you to be fully aware of it. But as you move forward, you're going to see that we're going to take these classful addresses and we're going to start borrowing bits from the host portion to increase the network bits. And we're going to end up with different notations so that we have the ability to more efficiently use our addresses. Okay, any questions on that? There'll be a bunch, I know, but as you move forward, it'll make a lot more sense as we move forward and you get into our IPv4 addressing and all those.
Now, with those, the classful addressing, I've always heard there's some type of security associated with like a Class A is more secure than like a Class B. Is there anything to do with that, or?
No, not at all. I've never heard anything about security being related to those.
Okay.
No. The one thing we will talk about more as we move forward is you will see that a Class A is a small number of networks with a bunch of hosts on it. Because it's got 2 to the 24th host. A Class B is a 16,000 networks with 65,000 hosts, and Class Cs are a large number of networks, around 16 million, with only 256 hosts per network.
Okay.
All right. And that's because of the number of bits left for the host bits and the number of bits that are being used for the network bits. Okay. Now, the other thing you're working on this week, folks, is this basic router configuration. I'm not going to spend much time on this simply because configuring a router with its basic configuration steps is almost exactly like a switch. You give it a host name, you give it enable secret password, you give line console passwords, line V2I line passwords, service password encryption, and banner message of the day. The only thing that is different on a router versus a switch is that routers, you place IP addresses on the actual physical interfaces. And remember, on the switch, we put it on our switch virtual interfaces. So that's the big difference on a router. So you actually go into the router. So for instance, on our 4321s, especially in NetLabs, on 4321s or 4221s, either one, we've got gig 000 and gig 001. And you go into those interfaces, and that's where you put your IP addresses. And the command is simply the same one as used for the switch virtual interface: IP address, the actual address, and the mask. But that's the only major difference between a router and a switch, is that where you place those IP addresses. The other one that I will tell you about, you need to just be a little bit careful with, is that on the router, typically we only have 5 V2I lines instead of 16. You know, on a switch, it's line V2I 015. On a router, it's just 04, because there's only 5 of them available. Now you can actually put in line V2I 015 on a router. It just creates 16 V2I lines. It actually adds V2I lines into the configuration when you do that, which is fine as long as you secure them with a password and the login command. So when you get into that, you'll see that a router itself is very simple to configure. It is the exact same commands as a switch, even the same modes. The only difference being where you place your IP addresses. Okay, folks, I'm going to stop with that. Let me stop my sharing. I'm going to stop my recording.